In this last lesson, we want to talk about ultimately the divergence theorem and Stokes theorem. In order to do that, we need to talk about something called a surface integral. So in Calc 3, we've talked about a lot of new types of integration that you didn't deal with in Calc 1 and Calc 2. In Calc 1 and Calc 2, you dealt with single integrals only, in which you integrated a real function over an interval. But since in Calc 3, we've talked about double integrals, where we integrate a real function over an area. We've talked about triple integrals, where we've integrated a real function over a volume. We've also talked about line integrals, vector and scalar line integrals, where we integrate a function over a curve or a vector field over a curve. So we've talked about integrating over a bunch of different things, over an interval, over an area, over a volume, and over a curve. And we've also changed what we were integrating over those things. And so in this last one, we need to talk about for surface integrals is integrating over a surface. So when you think about integrating over an area or a volume, well, let's talk about volume. So let's say we talked about integrating over that box. Okay, this was the volume we were going to integrate over. And really, it was the inside of that box was the volume we were integrating over. Now, if we talk about integrating over a surface, we're only going to integrate over the outside of that box. Okay, and we could talk about integrating functions over that surface or integrating vector fields over that surface. And what we want to really focus on is more or less vector fields over the surface. Because that has more use to us right now in these theorems. And so we could spend, multiple classes just talking about surface integrals and integrating functions over surface integrals and vector fields. We only have this last lesson to do it, so we're not going to do a whole lot of this integration, but we do need to talk about it. So let's say we wanted to integrate a vector field over a surface. So we want to do a surface integral for vector fields. Well, what that really represents is what we'll call flux. And it's basically the rate of flow through the surface, such as molecules through a cell membrane. So think about, water molecules through skin. That would be it. So here's a picture of, a surface here, and you have a vector field traveling through that surface. And essentially, we would talk about the flux, or the rate of flow through this surface in this vector field. Now, in order to do this, what we need to do is a couple of things. One thing we're going to really need to do is we need to parametrize the surface, which is not very easy to do. Okay, so that would be the one thing we would need. Another thing we need to do is we need to specify the orientation of flow in what we would call the positive direction. And we do that by finding a normal vector, say E sub n, at some point on the surface. We take some point on the surface, we could find the tangent plane right there at the surface, and then we could find the normal vector right there. Okay? And we could then represent the orientation of flow relative to the surface as we work through this surface integral. And so if we were going to do a surface integral, we would integrate a vector field with respect to the surface. It starts to look like a double integral with respect to the surface. We would do that by looking at it as a dot product between the vector field and that normal vector. So we look at the normal vector to the surface, we look at the vector field and do that dot product, and that's really how we would start to integrate it. But there's a lot of different pieces that would go into actually computing this. And this is where essentially the divergence theorem comes into play. There's a way to do this based off of things we've already discussed, where we don't have to parametrize the surface and look at the normal vector to the surface and integrate with respect to the surface. And so the divergence theorem will get us there. So in order to talk about the divergence theorem, we first need to talk about calculating what's called the divergence of a vector field. Okay? And we'll talk about how divergence theorem and Stokes theorem, which will come last. And the order here, we can go back and forth. Sometimes we'll do Stokes theorem first. Sometimes I'll do divergence theorem first. This semester, I decided to do divergence theorem first. So anyway, we have to talk about calculating the divergence of a vector field. So let's say you have a vector field here, and we have this 3D vector field. F1, F2, F3 are the components of that vector field. We wanted to calculate the divergence. Well, the divergence is essentially the sum of these three separate partial derivatives. You take the partial derivative of f1 with respect to x, plus the partial derivative of f2 with respect to y, plus the partial derivative of f3 with respect to z. And again, the notation would be just div of f, divergence of f. So let's say here's our vector field, and we want to calculate the divergence of this vector field. So if I did the partial of f1 with respect to x, that would give me the derivative of this with respect to x. So that would be what? Y to the xy. Okay, y is treated like a constant. Then we take the partial derivative of f2 with respect to y, and that would just give me x. And then we take the partial derivative of f3 with respect to z, and that would give me 4z to the third. So then the divergence of f would just be the sum of these three things. So ye to the xy plus x plus 4z cubed. So where does this come into play? Well, now we need to talk about the divergence theorem, okay? And you'll see where this comes into play. So the divergence theorem is essentially a way of calculating the flux for a vector field, integrating a vector field over a surface. Now, rather than directly integrating the vector field over a surface, similar to Green's theorem, we change this into an integral that we would have already learned. So you think about Green's theorem. We want to integrate a vector field over a curve. Instead of doing that directly, what we do instead with Green's theorem is we integrate a function over an area that that curve bounds. Well, this works a lot the same way in 3 dimensions. In that if we want to integrate a vector field over a surface, so let's say we have this surface, and the surface is a closed surface, so it encloses a region W. Right? Similar to the Green theorem, we have a closed curve where it encompasses an area. Here we have a surface that essentially is completely closed in. So think of it like this box that's closed completely. And we want to integrate a vector field over this entire surface. But the surface encloses essentially this volume, W. And assume S is what we call piecewise smooth and oriented by normal vectors pointing to the outside of W. So we have these normal vectors that are all pointing kind of to the outside here of W. And F is a vector field whose domain contains W. So the vector field essentially goes through this surface. Okay, so this vector field going through the surface. If we want to integrate this vector field over the surface, what we can do instead, divergence theorem says, we can instead integrate the divergence of F over the volume that that surface encompasses. So we could do a triple integral. The benefit of this is we already know how to do this. We know how to integrate a function with respect to a volume. It's a simple triple integral. I say simple, but it depends on how the integral ends up setting up to be. But this is something we know how to do. We do not have to go and learn how to do a surface integral, integrating a vector field over a surface or even a function over a surface, which we really haven't discussed, which is also not very easy. It would take us multiple lessons to get into, in that we have to parameterize the surface, we have to look at the normal vector to the surface, etc. So divergence theorem is, in a way, a offshoot of Green's theorem in that this is 3 dimensions and we're integrating a vector field over a surface instead of integrating a vector field over a curve. So you can see kind of how the relationship between Green's theorem and divergence theorems goes. We're going to calculate this, what we're looking for, in a different way based off of previous knowledge. Okay, so let's look at this example. we want to find the flux of a vector field, say F, which is calculated by zi plus yj plus xk, over this sphere that is a unit sphere, so has a radius 1. So this is the surface that we want to integrate this vector field over. Well, clearly this is a closed surface, so we're good there. And if you thought about this sphere and you looked at the tangent plane to the sphere, the normal vector would definitely be pointing outward the entire time. Okay. So we want to calculate the divergence of F. So the partial derivative of z with respect to x would be 1, plus the partial derivative of y with respect to y. Oh, made a mistake already. The derivative of z with respect to x would be 0, plus y with respect to y would be 1, plus x with respect to z would be 0, so the divergence here would just be 1. And if I wanted to integrate this vector field over the surface, I should instead integrate this function, which is 1, with respect to this volume. Well, now I'd have to define this volume. Well, I could do it in terms of x, y, and z and say, okay, what's z between, what's y between, and what's x between, and we can get done that way. In which case I'd have to split the sphere into the top half of the sphere and the bottom half of the sphere by solving this for z, and I would get negative square root of 1 minus x squared minus y squared, and positive square root of 1 minus x squared minus y squared. And then if I look at y and x, I would be basically looking at the circle. So I could do the same thing. If I just look at the circle and the xy, I could do the top half of the circle and bottom half of the circle. So negative square root of 1 minus x, and positive square root of 1 minus x squared, sorry. And then x would go between negative 1 and 1. And so I could integrate with respect to z first, y second, and x third. However, we could also define this sphere in spherical coordinates. I could change my differential to spherical coordinates. I could change my function to spherical coordinates. And I could define the region in spherical coordinates. That may be easier here. So if I looked at rho, phi, and theta, zero to 1 for rho, it's the radius. Phi is 0 to pi. And theta is 0 to 2 pi. And we've talked about this before. Okay? About this is a great way to define our sphere with spherical coordinates so we don't get in trouble with the phi issue. And then the differential is rho squared sine phi d rho d phi d theta. And so if we did this now with spherical coordinates instead of doing all this, I think we're going to get the easiest way through this problem. Because remember, this is just a triple integral, so once you get to the triple integral part, you do whatever you need to do to get the triple integral done. And we've learned a lot about integrating triple integrals. So we have this triple integral of rho squared sine phi d rho d phi d theta. If we do rho first, that's 0 to 1. If we do phi second, that's 0 to pi. And if we do theta last, it's 0 to 2 pi. And order doesn't really matter because everything's constant here with our integrals. I also have two single variable functions multiplied together, so I could break this out into 3 separate single integrals. So let me get some space in here. In which case, what I'm going to do is the integral from 0 to 2 pi of d theta times the integral of rho squared from 0 to 1 d rho times the integral from 0 to pi of sine phi d phi, all multiplied together. So this one's going to give me theta, so it's going to give me 2 pi. This one's going to give me rho cubed over 3 from 0 to 1, so this is going to give me 1/3. And this one's going to give me, negative cosine phi from 0 to pi. So we get 2 pi times 1/3 times, if I plug in pi, I'm going to get -1 with a negative is going to be +1 minus, what becomes plus, and cosine of 0 is 1 again. So I'll get 2. So I get 4 pi thirds. And so the flux of this vector field over the surface would be 4 pi thirds. But notice we didn't have to integrate the vector field over the surface directly, and that's the beauty of the divergence theorem. Here's another one. We're going to use the divergence theorem to evaluate this vector field over the surface, okay? Where here's the vector field in question, and the surface consists of, 3 different surfaces kind of all put together, making up this picture. So we have 4 minus 3x squared minus 3y squared. That's this surface there. Z is between 0 and 4 there, or for 4 and 1, so there's 4, there's 1, so we have that much of the surface. That's the top piece. X squared plus y squared equals 1 is this kind of bound down here. That gives us this little band around the middle, and that's between 0 and 1, and then the xy plane on the bottom to cut it off. So it's a closed surface. Seems like it's fairly complicated. But if we think about this as a volume, if I was to calculate this volume, it's really just this surface over this area. And so we could define this as, okay, Z is between 0 on the bottom and 4 minus 3x squared minus 3y squared on the top. X and y are bounded by that unit circle. That's this piece to keep us in this band here. So you could say negative square root of 1 minus x squared and positive square root of 1 minus x squared. That's the top and bottom half of the circle. And then we'd go -1 to 1. And what I'm talking about here is if we have this unit circle here, the top half of the circle is the square root of 1 minus x squared. The bottom of the circle is negative square root of 1 minus x squared. And that's just solving this for y. And then -1 to 1 on the x's. And so that gives us the circle piece. That gives us this band here. We have this volume here. We have what the x's and y's are stuck between. And we could define that volume this way. And so that's what we're going to need in order to integrate this vector field, because if we want to integrate the vector field over the surface, we're not going to do it directly. What we're going to do is we're going to calculate the divergence of f, in which case we would integrate this with respect to x, which will just give us y, plus this with respect to y, which would give us what? Minus y. And this with respect to z would give us 1. So add it all up, we get 1 again. Coincidence is not always going to happen. And so we're going to do the integral, the triple integral of 1 with respect to z first, y second, x last. Because of the way we define this, z is between 0 and 4 minus 3x squared minus 3y squared. And y is between negative square root of 1 minus x squared and positive square root of 1 minus x squared. And x is between -1 and 1. Now, we could leave this in x, y, and z and try and get through this integral this way. We could switch coordinate systems, in which case spherical is probably not a good idea, but cylindrical might not be a bad idea. And cylindrical, z stays z. But what we can do is do the first integral, and then in which case we have a double integral left over, and we could switch to polar coordinates once we get to that point. So we have all these options in this. I think we leave in terms of x, y, and z first and see how far we get, because the integral with respect to z is not going to be hard here. All right, so let's get rid of this. In which case, the integral with respect to z is just going to be z. So I still have this negative 1 to 1. I still have this negative square root of 1 minus x squared, positive square root of 1 minus x squared. I get z between 0 and 4 minus 3x squared minus 3y squared. I still have dy and dx. So if I plug this in for z and 0 and for z, it's really just going to give me this. So now I'm at this double integral, negative 1 to 1, negative square root of 1 minus x squared, positive square root of 1 minus x squared, and I have 4 minus 3x squared minus 3y squared, dy dx. Now, like I said, I can choose to continue down this road of y and x. Or at this point, I could switch this remaining double integral to polar coordinates. Now, I think that would give us the best option to move forward, in that when I start looking at integrating this with respect to y, this one's going to give me a y cubed, okay, right here. And then I'm going to be plugging this in for y cubed, so I'll have the square root cubed, and you can see it's going to get kind of messy. So if instead I switch to polar coordinates now, remember, this is the unit circle. So in polar coordinates, r would be 0 to 1, and theta would be 0 to 2 pi. The dy dx would be r dr d theta. And then it's just a matter of this function. Well, think about that. If I factor out the negative 3, I got x squared plus y squared, in which case I can convert that into 4 minus 3r squared. And so now there's my function, there's my differential, this is my limits of integration. Getting the rest of this done with polar coordinates, not too bad. Probably better than leaving it in x and y. So I'm going to do that. So I'm going to go 0 to 1 on the r, 0 to 2 pi on the theta. My function is 4 minus 3r squared, but I have an extra r in my differential dr d theta. So this r is going to distribute into there. And this becomes a very simple integral, especially a simple double integral. So again, we have this 0 to 1, 0 to 2 pi. If I distribute that r, it would be 4r minus 3r cubed dr d theta. I would have 0 to 2 pi. So if I did with respect to r, I would get 2r squared minus 3r to the 4th over 4 between 0 and 1 d theta. Then I would have, 2 minus 3/4 d theta. So 2 minus 3/4, what would that be? 8/4 minus 3/4 would be 5/4. So 0 to 2 pi, 5/4 d theta, which would give me 5/4 theta between 0 and 2 pi. So 5/4 times 2 pi would give me 10 pi over 4, or simply, 5 pi over 2. So the integration of that vector field over the surface that looks fairly complicated, and think about it, if we had to parametrize that surface and integrate the vector field over the surface without even knowing how that's done, because we haven't learned it, you could probably assume it's not going to be as easy as what we just got done doing. But this was not bad, and we're using things that we know already without really getting into the concept of a surface interval. All right, so then we have Stokes Theorem, which is the final one, and this is where really not having time to cover surface integrals is going to play a bigger role. in that, Stokes' theorem is kind of the next dimension up version of Green's theorem, and you can really think of divergence theorem is really similar to that, but the difference is in divergence theorem, we're not integrating over a curve anymore, we're integrating over a vector field over a surface. Where Stokes' theorem, we're still going to be integrating a vector field over a curve. So we're still going to be doing, not necessarily, we're not going to be calculating the flux, we're still going to be calculating the work done by force in that regard. So, because it's a vector line integral. So if we think about Stokes' theorem and Green's theorem, Green's theorem relates the double integral to integrating over an area, okay? Where Stokes' theorem will relate a surface integral instead of integrating over a curve. So if we think of, here's a couple of surfaces, and these two surfaces here and here are open, and this one is closed. Okay. If you think about an open surface, it means there's a way to get from the inside to the outside. Okay. So you think of the outside of the surface, and then in here would be the inside of the surface. And if it's open, you can go in and out. And sometimes you have multiple openings where you come in this way, come out that way, etc. But this one, you're either on the outside of the surface or you're on the inside of the surface, in which case it's closed. And this is what we'll need to talk about with Stokes' theorem. It's the same thing we need for divergence theorems too, right? We were talking about integrating over a closed surface. In order to work with Stokes' theorem, we would also need to talk about the curl of a vector field and calculating the curl, which is essentially the determinant of a matrix, in that if we have a vector field that is a three-dimensional vector field, if we create this determinant and calculate this determinant, ijk as the first row, the partial derivative of something with respect to x, the partial derivative with respect to y, the partial derivative with respect to z, and then f1, f2, f3. And we do this determinant. So what do? We do the I component, and we do this 2 by 2, which is the partial derivative of y for f3 minus the partial derivative of f2 with respect to z, and then so on. Keep doing that. That would be how we calculate the curl of f. And this is something we would use in Stokes' theorem. Because instead of directly integrating a vector field over a curve, we're going to try and do it a different way. So let's calculate the curl first for this vector field. So if I set up this I, j, k, partial with respect to x, partial with respect to x, partial with respect to y, partial with respect to z, and then f1, which I'll fill in here as xy, and f2 is e to the x, and f3 is y plus z. And so if we do the first set, we do the partial of this with respect to y, which will give me 1 minus partial of this with respect to z, which would give me 0. So that's the first one, that's your I. The next one, we always put a minus in front of it. And since it's the j component, it's this one and this one. So we do the partial with respect to x for this, which would give me 0, minus the partial with respect to z of this, which would give me 0. That's my j. Plus third one, get rid of this, is the k component, so we use this. So the partial with respect to x of e to the x would be e to the x, minus the partial with respect to y of x times y would just be x, and that's my k. So ultimately what we get here is I, j is 0. If you want, we could write plus 0j. You can say minus, but minus or plus 0 doesn't really matter. and then plus e to the x minus xk. And so that would be the curl of this vector field. Now, why is that significant? Because that's how we're going to use Stokes theorem. So for Stokes theorem, if we have a surface that's oriented piecewise smooth and bounded by a simple closed piecewise smooth boundary curve. So of those different pictures, you had this picture. We had this open surface, okay, and it's bounded by this single closed curve. Remember, there was this other surface that looked like this, okay, and there were multiple curves that bound the surface. This is what we're not talking about. This is what we're talking about. So it's an open surface that's bounded by a single, simple closed curve. And let's say we want to integrate a vector field over this curve. Okay, we want to integrate a vector field over this curve, but that curve happens to be the opening of this surface. Okay, rather than integrating the vector field over the curve, that essentially is the opening to the surface, what we could instead do is integrate the curl of the vector field over the surface here itself. Now, the problem with this for us is that it would require us to learn how to do surface integrals, which again would take multiple classes to get into, and we just don't have the time to do that this semester. But talking about Stokes theorem, I think, is just as important in that we don't directly integrate the vector field over the curve. You know, we've seen this multiple times now, that instead of directly integrating the vector field over the curve or integrating the vector field over the surface, we convert it to something else. In Green's theorem, we're integrating a vector field over the area that the curve bounds, but that only works in 2 dimensions, right? That's if you have a 2-dimensional vector field and a 2-dimensional curve. Here what we're doing is we're bumping that up to 3 dimensions. And we're saying, well, we want to integrate a vector field over a curve. And that curve is the opening to a surface. It doesn't bound an area. We're not talking about the area it bounds. We're talking about that curve being the opening to a surface. So if I want to integrate this vector field over this curve, and that happens to be the opening to this surface, instead of doing that directly, which may not be computationally easy to do, we could instead try to integrate the curl of the vector field, over the surface for which that curve is the bound, or the opening, I should say, of the surface. Now, this is not easy to do either, right? But the idea that there are other ways to do this is the important part. So out of the 3 final theorems, Green's, Divergence, and Stokes theorem, Stokes is the only one that we really don't necessarily have the skills right now to do without spending quite a bit of time with how to calculate a surface integral. With all that being said, here are essentially our fundamental theorems of calculus. There's the first one, which took you all the way through Calculus 2, which said, okay, how do we integrate a function over an interval without having to do all that summation business that you started with in the definite integrals? And the idea was find the antiderivative, plug in b, plug in a, subtract them, and you get that. And we saw all different applications of that, from calculating area to even calculating volumes, some work done by force problems. Think of all the applications you learned throughout Calc 1 and Calc 2. Then we had our fundamental theorem for line integrals, okay, which was integrating a vector field over a curve. And this is for conservative vector fields. And it was all about having the potential function, that's why it had to be conservative, and evaluating that potential function between essentially the endpoints of the curve, starting point and ending point, and subtracting. And these two were really closely related. Then we have Green's theorem, which is integrating a vector field over a curve as well, but instead integrating the vector field over the area that that curve bounds. Then there's Stokes Theorem, which is integrating a vector field over a curve also. Okay, so really all three of these are doing the same thing, right? These are all for vector fields over a curve. And instead of doing that, we're going to integrate a curl of the vector field over the surface for which the curve is the boundary. And then finally, the divergence theorem, which is not integrating a vector field over a curve, but instead integrating a vector field over a surface, in which case we're going to calculate the divergence of the vector field and integrate over the volume for which the surface bounds. Now, the significance of all these is that we don't do any of this directly. Okay? We find another way to get the job done, and that's why they're all related to each other. They're all doing different things. I mean, this group is all essentially calculating the same thing here, but this is integrating a real function over an interval. These are integrating a vector field over a curve, and this is integrating a vector field over a surface. But ultimately, the relationship that they all have is that we don't directly do any of these integrals. You know, if we wanted to directly do this definite integral back in Calc 1, the way you did it was with summations. And we don't do that. I mean, we did that for a short period of time, but really this is the way we got it done, was through antiderivatives. And the same goes for each one of these theorems. Okay? And so that's why we call these the fundamental theorems, in that they all have this relationship of, we don't directly calculate what we're really trying to find, in that there are ways to do that, right? We do have ways of directly integrating a vector field over a curve. And that was the first thing we talked about when we talked about work done by force, is how to do it directly. But we came up with these other ways of getting the job done, depending on what type of vector field we have, what type of curve we have, etc. And so that's pretty much the culmination of Calculus 3.